Hi, my name is Alicia Martin, and I'm a program manager at Google. Presenting with me is Tobin, a researcher and software engineer at Google. We're very excited to talk to you about some of the incredible research that our team is doing to support individuals with non-standard speech be better understood. And so today, a lot of the speech recognition technology relies on a lot of training data in order to work. Unfortunately, a lot of that training data comes from individuals or users with standard speech. And so for the 250 million people worldwide who have non-standard speech, a lot of the speech recognition technology or voice-activated technologies may not work well for them. And so in 2018, Project Euphonia was launched. We decided to launch Project Euphonia in partnership with the ALS Therapy Development Institute for the purpose of research and research that supports individuals with non-standard speech. This trusted tester program allowed us to gather some feedback on early prototypes. And then in 2019, we decided to make this program more broadly available to anyone that qualifies. The way that it works is that anyone with a mobile phone, tablet, or computer can access Project Euphonia, a web-based audio tool, in order to start recording phrases. We ask participants to record anywhere between 300 to 1,300 phrases, depending on the language. And these phrases are typically in categories. These are two of the categories of phrases that we ask participants to record, which are typically corresponding to key use cases. One of these categories is how individuals interact with technology. So for example, if I'm having a conversation with a Google Home or Google Assistant, asking Google Assistant to stop the music. The other category of phrases is how individuals interact with other people. These are conversational phrases. And so, for example, if I were to be speaking to a caregiver and I ask the caregiver to turn on the TV for me. It's because of the many contributions from our trusted testers and all of these organizations who have contributed to Project Euphonia that we've been able to do some transcending research to support individuals with non-standard speech. And today, we're incredibly excited to announce that we're expanding our data collection efforts to more languages, including Spanish. There are over 400 million Spanish speakers worldwide. Spanish is also considered to be the second largest language in the United States with over 33 million speakers. For this reason, we've decided to partner with several organizations in Latin America to make technology more inclusive for users, including the International Alliance of ALS. And so in the next presentation, Tobin will talk to you about some of that research to help individuals be better understood.
So previously, we've presented work on adapting end-to-end speech recognition models, particularly RNNT models that are recurrent neural network transducer models, which are the ones that can run on your device, your phone or your tablet. What they do is they take audio waveform, just a recording of your voice, turn it into some visual representation, such as a spectrogram, and then send that to the encoder. And the encoder then uses that as the input signal, and also uses the context from previously transcribed tokens, and combines those two signals to then predict the next token or word in the sequence. So that is what runs on your device right now. And for individuals with, let's say, dysarthria, what we found to be the best recipe to make those models work, particularly for one individual, is to tune and adapt just the encoder portion of this model using a relatively small amount of data. So we've taken a pre-trained model, which is around trained with hundreds of thousands of hours of speech data from several thousands of participants, and then only tuning just the encoder portion for one speaker using maybe 20 minutes of speech data can yield very, very pronounced results and improvement in accuracy. Through feedback from the Trusted Tester program in Project Euphonia and from users of Project Relate, we found that there are certain limitations to that personalization recipe. Particularly, one is for not intelligibility is not a constant, especially for individuals with degenerative diseases such as ALS. So as you can see here, we have on the right, we have speech decline in bulbar onset ALS. And as we see the around 9.4% per month in intelligibility decline. So that makes it difficult because when you train with data that at one level of intelligibility and then intelligibility degrades, then that makes the model less accurate on where you are now. So we have presented research on mitigation strategies for that. So be sure to check out that. Other issues are for some users, recording 20 minutes of speech data is not inconsequential. It can be almost intractable for certain people. So we wanted to be mindful of that, and we know that ideally this should just all work out of the box and not require any intervention from a user. So that is what I'm presenting today is towards that, is a step towards that. And then finally, as we've said before, this data we've collected is all users reading prompts, and though that may be helpful, especially in situations where you're talking to a virtual assistant or where things are more structured. In real conversation, things are much less structured, and we wanted to make sure that whatever we train is useful in many contexts, not just having short transactional phrases, either with technology or with other people. So to address this limitations that we found from personalization, the Euphonia research team, we shifted our focus from personalization to speaker-independent ASR, which, or as we'll say later in the slides, SIASR, which is basically trying to not focus necessarily on improving speech recognition for one user, but for all users at the same time. So out of the box, they'll be able to use and benefit from speech recognition technologies, no matter their level of dysarthria or how typical their speech is. So to that effect, we had to kind of come up with two strategies. One, we needed to find a data set, which we already had, but basically ensure that the data that we trained with was sufficiently large and specifically diverse and representative of the many etiologies that we've collected so far. Because as I said before, these models that we are adapting have already been trained with hundreds of thousands of hours of speech data from primarily from people with typical speech. And so we wanted to make sure that we also have, a large and diverse data set to adapt with. And we also wanted to test and make sure that our models are working for the use cases that individuals will use speech recognition for. So not just for, talking to a virtual assistant or having transactional phrases, but actual and real conversation. So I will go into that now. So taking the large Euphonia data set, we wanted to basically create a training portion and a test portion where there was no overlap between either any speakers or any phrases. What we didn't want to happen was that we thought that a model was getting very, very, very good, but then it turned out that it was just learning how one particular speaker was speaking, or it was just learning one particular phrase. So it's very important to have no overlap there. And also we wanted to make sure that we were utilizing as much of the data as possible, just because when you start slicing and dicing, some data will be left out. And we wanted to work to make sure that we were achieving our goals where we were using a large and diverse data set for training, and also testing on a large enough and diverse enough representative test set. So that's what we ended up with are the stats shown in this slide. So our test data is 200 speakers and around 5,700 utterances, and our training data is 1,200 speakers with almost a million utterances. And then there's a small portion of around 350 utterances from 24 speakers that we can just use basically to track how well the model is doing as it's training, which we call dev data. So check out the blog post here, and there will be a QR code at the end to understand more about this. We also created a real conversation test set. So this data is unprompted and spontaneous speech that our trusted testers recorded using in real-world usage of a personalized ASR model. We worked with these trusted testers to record them speaking, and then speech language pathologists reviewed all the data, removed any personally identifiable information, and then transcribed it. So this data set is this is 29 speakers and around 1,500 utterances that we can then use to measure how well our models are doing in real world conversation. So here are the results of fine-tuning USM with our data set. You can see USM's word error rate as the red bar in the middle of the two clusters. On the left, you see our prompted speech word error rate. Going from red, which is USM, adapting is the yellow bar. We can see accuracy is improved by 32% on prompted speech and 44% on conversational speech. The blue bar is a previous model trained with YouTube data, and it's there just to show what a smaller model that's not 2 billion parameters, just the effect of a model growing in size can have. And so what we're seeing is that this is a large win because it's a model that's more accurate for individuals with atypical speech, and it required no recording by one particular individual. It just worked better out of the box. However, if the model is still not serving a particular individual, we still say that personalization to one person's voice will be the best chance of having a speech recognition model recognize that particular person. So here's a couple examples of a trusted tester speaking extemporaneously and the different models' predictions of what was said. So we have the ground truth, which was what was actually said, and then the different models' predictions. So let's start with the first one.
I now have an Xbox adaptive controller on my lap. I now have an Xbox adaptive controller on my lap.
So we can see the L and the M in the fine-tuned USM is able to differentiate a little bit better, but they're very close. And then the second one.
I've been talking for quite a while now.
And here's something that is very typical for models that haven't been trained with any atypical speech is they just truncate and don't recognize or transcribe any speech it doesn't recognize. So as you can see, only the fine-tuned USM was able to transcribe I've been talking for in this space. But again, both truncate on let's see. So there's more work to be done. But as we can see in the data here and in the previous slide, there is a significant lift in accuracy. Thank you very much. Full details can be found in the blog post by following this QR code here.
Thank you very much, Jimmy and Alicia. So we are ready for questions now. Any questions? Gethin, one question here.
Gethin Thomas, MD Australia. Thank you for that. So the last conclusion was there's still a bit more work to do. How are you going to do that, or how much work is there more to do on this? Is it just putting more and more data through it so it gets better at learning, or is there a different approach you need to do?
Thank you for the question. Yeah, so I think there's a couple things that we really are interested in. One is, English is great, and we love English, but people speak other languages, and this USM Universal Speech Model is able to recognize 100 languages. So, getting better at those languages it requires data. So getting better at English will require more data. Getting better at other languages as well. Two, or I guess there's three things I want to talk about. Two would be specifically, making sure that it's not just American English that we are targeting, and that we are making collecting representative data sets and representative words that are important to different communities. So. I believe Richard Cave has spoken earlier at this event, and he's done a lot of great work in Ghana and in collecting data there and collecting feedback about how these models work and how there needs to be improvement for the phrase sets there that we use. And I had a third one, and it is and finally, what I showed was some bar charts of word error rate, and that is basically about how perfectly is that speech model transcribing exactly what you have said, but through feedback from working with people with ALS and MND and other neurological conditions, just being understood, being comprehensible is more important than exactly getting it exactly right, especially when you're in a conversation and the goal is just to be understood. So we're working and have published work on how to evaluate these speech models for comprehensibility rather than syntactic accuracy, or so that's kind of what we're working on and the next steps. Thank you.
Okay, I believe we have two more questions. Jen?
Can it remove the snap in her speech?
Can it remove the snap in the speech? Can it remove the snap in the speech?
The snap in the speech?
Slur.
Slur. Yeah.
The slur.
The slur.
Oh, sure. So this is a recognition model and just for transcription. So it's not transforming or playing back anything, such as the repeat function in Project Relate. So it's the purpose of this is to listen to the speech and transcribe it, whether or not there is slur present. But there are other technologies that other teammates on my team are working on for voice transfer or the repeat function in Relate. I hope that answers your question.
Did? Yes. Okay. I have one more question here from Marcela.
Well, this is basically Marcela from Marcela, Colombia. This is just basically a comment. We started working with you guys to get people from Spanish speaking to start recording their voices. And it's been amazing. Patients are really happy because usually we don't have voice banking in Colombia, first of all. So usually when we talk with the patients that already have dysarthria, they're like, there's nothing we can do. In this case, there's nothing they can do for themselves, but they know they're pitching in for a future patient with ALS. They will be understood in future years thanks to this type of technology. So this is just a thank you for thinking in Spanish-speaking patients, and just like everybody work together so we can actually improve lives and quality of life of patients with ALS all over the world. So thank you.
Yes, thank you. I've been on the team for 5 years now, so this is a important thing to work on. Thank you.
We still have time for a couple of more questions. We don't? Oh, okay. Okay. Thanks again, Jimmy. Thank you so much.
Thank you.